Unit 2 Chemistry, Chapter 3, 2. So here we're going to look at the differences between the main group and the transition elements, both in terms of their structure and also in terms of their reactions. There are some similarities, there are some differences. So when we talk about main group elements, we're talking about the ones in yellow down here. We're talking about ones that are in P block or S block. Okay. Transition metals, we are talking about these ones down here, which are in the D block. Obviously for the P block, some of these are metals, some are non-metals. Okay. For S block, these are all metals, and for transition, they're all metals. Okay. Those that are in yellow, the main group elements, are much more abundant than the transition group. So there are more of these, but these ones you find in a greater proportion on the Earth naturally occurring. For the S block and the P block, we can predict really reliably the number of electrons in their outer shell, and therefore we can predict really reliably what their bonding is going to be. Okay. For transition elements, they're all D blocks, so they all have an unfilled d orbital. And if we remember, those d orbitals are very, very close in energy to the S shell, which is orbiting them. That makes them less predictable. They can make a range of different compounds. Okay? So they've got 2 electrons in their outer shell, which are in the S subshell. But then when they react, they can lose electrons from more than one shell, and they can also shift electrons down from that S subshell into the D subshell. Okay? Because of that, they can have different charges depending on what they're reacting with. So you can have copper 1+ or copper 2+. They both exist. Okay? Now, you don't need to worry about being able to figure out which one you're going to get in which circumstance. Okay? You do need to just accept and understand that they can have these different charges, and therefore that when we're naming them, we need to put their name, the number in Roman numerals that indicates their charge. So you'd write copper 1 or copper 2. Okay. So generally, we're losing the outer shell electrons, but they can lose their d electrons too, but that requires more energy. Okay. So iron, for instance, it's got an electron configuration which is argon, plus then you've got 3d6 and 4s2. If it makes 2+, it just loses these 2 electrons. But if it makes Fe3+, it loses these 2 electrons plus 1 of them. That gives us a half-filled D subshell, which, as we know from our copper and chromium exceptions, remember, a half or a fully filled D subshell is more stable. So that's why it quite likes to do this, as well as liking to do that. Now, all metals, whether they're transition block or main group, will react with water, with acids, and with oxygen. Right? If they react with oxygen, they make the metal oxide. So magnesium and oxygen makes magnesium oxide. Note that we're using the IDE ending because that tells us that it's in a compound. If we're reacting with an acid, all acids have got hydrogen in them. We'll look at what makes it an acid later on, but they've all got hydrogen in them. And when they react, that hydrogen is given off as hydrogen gas, which remember is one of our diatomic gases, so H2. All acids, as well as the hydrogen cation, have also got an anion. In this case, it's the chloride ion. That chloride ion, or whatever the anion happens to be, reacts and combines with the metal to make an ionic salt. So when we say salt is made, we don't mean it's always sodium chloride. We mean it's always the metal with the anion from the acid. If we react it with water, we always make the metal hydroxide, and we always get hydrogen gas as well. Now we can use these reactions to start thinking about how to extract them from their ores. So a metal ore is the naturally occurring source of a metal. They don't normally exist as pure substances. Some of them do. Your really unreactive metals, the precious metals. So you can find gold nuggets, for instance. Not easily, but they can be found. But ones that react much more readily, like aluminium for instance, would exist as a compound. So commonly you might see them as oxides. So bauxite is aluminium oxide, hematite is iron 3 oxide. You might also find them as sulfides. So you can find iron sulfide, okay, or iron 2 sulfide, or you can find it as something which is a bit more complex. So this is an ore which has got both copper and iron in it, as well as a sulfide. I'm not going to try and pronounce it. So to extract them, what we're wanting to do first of all is firstly get rid of the rocks that are around it, crush it, physically separate it. Okay, you might use some kind of flotation device for that. And then, once we've got the compound separated from all the junk rock, then we react it. Okay? Essentially what we do is we want to add electrons to the ions, because remember, when a metal has reacted, it's given up its electrons to become the metal cation. So what we want to do is give them back those electrons, and that will then turn them into the pure element. So we call this process reduction. So when they gain electrons, it's called reduction. We can do this using a number of different methods. We can use a more reactive metal, and that will give up its electrons. We can also use carbon. Carbon quite likes to give up its electrons. Okay. We're then, of course, sacrificing something. The alternative is we can use an electrical current, because an electrical current is a flow of electrons. So we can simply pass electrical current into it and use that to break them apart and give the electrons to the metal.